And actually, having gone through at least 2 string revolutions, I feel that the period that we are now undergoing is close to the beginning of yet another revolution. Usually the revolutions are inspired by theoretical breakthroughs in string theory, and I hope this one is actually experimental breakthroughs. At least that's my hope. We are on the verge of a very exciting period in particle physics. Interesting results are coming out from LHC any moment now. Who knows which direction they will go, but certainly string theory should be ready to try to connect it to ideas in string theory. And so hopefully this workshop goes in that direction, and we'll see where it takes us. So anyhow, with that, I would like to start my talk related to F-theory phenomenology. And I thought it might be a good time to reflect on what we have learned or what we have yet to do for F-theory phenomenology. So, so F-theory has been studied by many groups, and many talks in this particular workshop we'll hear about. In fact, there are so many works that I'm not going to give any references basically in this talk, so I apologize. But basically, my main point is just to have a kind of a reflection on ideas rather than specific papers. So I'm not trying to give that. That's why I'm apologizing. But many interesting and diverse ideas have already appeared, which I want to review. So the first thing is, slide is interesting. I think that might help me with this.
You better read it out loud.
Yes, I guess so. I thought the black and the bright color would be the best contrast. I guess not. So the enormous landscape of vacuum with n equals to 1 supersymmetry. I mean, one hears this number 10 to the 500 quoted all the time. I don't know exactly where that comes from, but nevertheless, it's clear that the bulk of it in any form that you can count is related to these kind of constructions. So that actually is very good in terms of constructing vacuum for string theory for sure with n equal to 1 supersymmetry. So that's one motivation, perhaps, for studying these kind of theories. Grand unified theories is very naturally incorporated in these theories, and I think that's probably one of the main important points of these theories. We believe in grand unified theories. In fact, I think one of the lessons that particle phenomenology has learned, even though we don't have a proof that grand unified theory works, the aesthetic reasons for gut, and in particular concrete evidence like neutrino masses and gauge coupling unification or almost unification, points in the direction there is a grand unified theory, forgetting even about the aesthetics. So it seems like we have to take that very seriously and take that as a starting point in any string construction. And that's very naturally incorporated in F-theory. Another aspect is that in these phenomenological models, local descriptions of the theory of the compactification is to a large extent all one needs to get started. At least that's for one class of assumptions that one tries to connect to real world, is that the local data are all what we need, and that's useful because local data are easier to characterize than global data. Flavor physics emerges very nicely, and there are many different ways it can happen, but it seems like we have very nice ideas emerging from these constructions for describing how the flavor hierarchy appears. And then, that's getting better, thank you. Concrete mechanisms to break supersymmetry have been advanced in this context. And aspects of gauge couplings unification or misunifications, of how they can unify or what kind of exotics could there be around, also have been studied. And furthermore, interesting additional sectors in these theories, conformal sectors, have also been incorporated. So we seem to have gotten to and there are many other things I'm not even mentioning. So it seems like we are in good shape, and so what remains to be done? Well, in fact, we're just getting started, in my opinion. In fact, all of them, we have just basically scratched the surface of all of these, but really not developed it far enough. So in some sense, we really have to develop all of these in order to really understand how or if the F-theory phenomenology can make contact with particle physics. So let me try to go over some aspects of these potential developments that we can do. So as I mentioned, there's an enormous landscape of vacuum with n equals to 1 supersymmetry, and F-theory, the reason it has an easy time in constructing these vacuums is because it makes a connection with Calabi-Yau fourfolds. And in particular, elliptic fourfolds are a large class of Calabi-Yau, and therefore you can construct a lot of vacua, and then you put fluxes on it, and there you go. You have a huge amount of possible vacua with natural superpotentials and all that can appear in these theories. So that's already nice. And what's good here is that holomorphy, which is one of the hallmarks of supersymmetry, is naturally incorporated in the construction of the vacuum. Now, so we can use a Calabi-Yau fourfold. So what's the problem with this? Well, we have to put some restrictions, and one restriction, which is not very strong, but at least it's something that we can start with, is to characterize all of them which are forced to have at least an SU5 symmetry, SU5 singularity to give us an SU5 gate symmetry. That's the least you could have for a grand unification. Now, what I mean by forced, what I mean is that the geometry should not allow you to get rid of it. In other words, they're forced to have at least an SU5. And there are examples of this that we're familiar with, for example, in the context of compactification of F-theory on elliptic threefolds, when the base of the Calabi-Yau is related to the four-dimensional Hirzebruch surfaces, you can have, depending on what kind of Hirzebruch surface you get, the elliptic Calabi-Yau over it will have singularities. And so this corresponds to the ideas that we all understand in terms of counting the dimension of the moduli space, plus dimension of Higgs space, and so forth in the six-dimensional theories. And it's natural to try to incorporate these in the context of one lower dimension, one complex lower dimensional situation, which involves Calabi-Yau fourfolds. This has not been done. So already trying to mathematically characterize what does it mean to have SU5 symmetry from the viewpoint of F-theory in terms of some global aspects might be potentially interesting. Locally, of course, we can say it. Grand unified theories are naturally incorporated here, and as I mentioned, we can have a big enough gauge group like SU5, and the way this can happen is that we have a 7 brane in these theories which have an appropriate gauge symmetry on them. So, for example, we can have a 7 brane which carries SU5 gauge symmetry on it. And we can have interesting intersecting branes could have matter arising on the curve to intersect, and the triple intersection giving, if you have these matter curves intersecting over points, giving the Yukawa couplings. However, as has been understood, is that the top Yukawa coupling, the Yukawa coupling which gives the top quark its mass, has to have an E-type enhancement. And that's remarkable. In other words, that's an aspect of phenomenology which in string theory is, I think, very interesting, that if you say to phenomenologists we have an SU5 gauge symmetry and we have a mass for the top quark, they would not say immediately, E groups. But in string theory we should say, E groups. So as soon as SU5 comes into this game, in some sense exceptional groups are part of the game simply just because you want to get the right Yukawa couplings. So in some sense, F theory unifies the idea of grand unification to the matter sector and to the Yukawas, and basically to enhancement of gauge symmetry on the loci of internal geometry of string theory. So in some sense, the unification in the geometry, in pieces of the geometry, is what F theory is doing, and in some sense, it gives us some new insights into what unification really means. And in this particular case, the existence of E structure. So in particular, if you want to have 10-10-5, we know that you have to have at least an E6 point in your geometry, a point where you have an elliptic singularity of E6 type. Now, local data may be all one needs for applications, and in fact, we don't know if that's really the case or not, but if we assume that gravity can be decoupled, and what I mean is that if you can assume to have a particle physics spectrum in which questions of gravity does not, that you can imagine having a particle physics even if M Planck is infinite, which in principle we think we should be able to have, but it's not guaranteed, then that means that the question of gravity cannot be that major in understanding the structure of the matter or unifications and so forth. And if that's the case, we're lucky because then the structure is going to be much easier. Global questions means gravity questions. So if we don't have to worry about that, then global questions which are typically hard might be ignored. Of course, at least that can be ignored maybe at first pass. Of course, we cannot fully ignore it. We do want to have gravity at some level. So we cannot completely forget it, but at the first pass we can ignore it. So we basically take the local data, the point of Ikawa interaction, the curves, which give you the matter, and then the surfaces, which give you the gauge symmetry. And we seem to be set, except that we have to need some extra data here. It turns out that these intersecting matter curves, which give you the intersecting branes, which gives you the matters on the intersection, have more structure than meets the eye. It's not just the geometry, and it's also what particular gauge fees live on this intersecting, near the intersection geometry. And this turns out to be very non-trivial, and it's called T-branes. And it turns out that it's very, very non-trivial, and not arbitrary T-branes seem to be globalized. But it's not known exactly what kind of local data of intersecting branes can or cannot be globalized. So this is some work that has to be completed, understanding the structure. So of course, if it cannot be globalized, we can call it swampland, but we would like to know which ones are the ones which cannot be completed. So just as an example, it was already understood that when you talk about intersecting branes, for example, if you have two branes, you can think about having an SU2 gauge symmetry if they are parallel. And if they are not parallel, you can think about giving a web, which if you think about the x as the separation of the branes, you can think about them as some kind of breaking of an SU2 to U1. But it was understood that you don't want to have just the regular intersections as we are familiar with in usual branes, but we want to have intersection with monodromy, which in particular means that you would naively want to have a structure which looks like this as you go around the 2 pi. You don't come back to itself, but reflected in this way. It was understood that this is not the right way of saying it, but actually this is the right way of saying it. You want to have an SU2 structure where the geometry looks like 0, 1, x, 0, which any place away from x equal to 0, it can be diagonalized in this form, but at x equal to 0, these two matrices are not equivalent. So this is the right description, and this is called a T-brane structure. So understanding these kind of monodromies turns out to be crucial for understanding flavor physics in particular, and other things in the context of FTL phenomenology. So this is already interesting, even forgetting about questions of particle phenomenology, for understanding aspects of string theory and what the brain intersection really mean. This has to be developed even further. So some aspects of T-branes we understand, but it would be worthwhile understanding them even more. Now, flavor physics emerges naturally in FTL, and there are many ideas in this direction. There are many different ways of doing it. But the basic idea is to try to use local data to try to understand the flavor hierarchy. The one particular way I like is basically starting with a leading order rank 1 mass matrix, which seems to be very natural for phenomenology. That's the limit in which, to leading order, you have the top quark mass being at the weak scale and the other quarks being massless. And this is natural because in the context of FTL, it simply translates to having minimal intersection numbers. So that's nice to have. And for example, if you want to think about it like this, you have, let's say, these red curves corresponding to the matter and the blue curve corresponding to the Higgs. You have some interaction like this. And if you take the zero modes corresponding to the matter on each of the curves and taking the inner product between them, the overlap, since they intersect only at one point, the matrix of the 3 modes living on each one of them will give you a structure roughly like this, where there's only one overlap, where the wave function, which doesn't vanish at that point, has overlaps with the other wave function, which doesn't have a vanishes at that point, and any other ones which vanish at these points will have no overlap. So you naturally have a rank 1 structure, and you can use the rotational symmetry of these curves to build in it the Frobat-Nielsen symmetry. Again, it's a beautiful fact that Frobat-Nielsen U1 symmetries become naturally identified with the rotational symmetry of these curves, which are approximate because they're not exact symmetries of the geometry of the Calabi-Yau, but approximate ones, as Frobat-Nielsen symmetry must be, and also has a natural meaning of where these U1 symmetries come from. So the U1 symmetries that Frobat and Nielsen have are the extra two of the extra dimensions of string theory, at least near that point. So that's an interesting interpretation of the meaning of the U1 rotations of the Frobat and Nielsen. It's a geometric rotation. And using these ideas and so on, one can come up with kind of pictures like this, where you can have an estimation of CKM matrix in F theory, where you can have, where you relate basically the estimates to a simple volume of these 7 branes and curves, and the alpha gut controls the volume. 1 over the alpha gut is the volume of these internal geometries. So using that, you can actually get an estimate, and these are just estimations of what it looks like, and you get some regional looking similarities, and some people have noted that this is probably too good, but what can I say? And you can also do the same thing for leptons, and you get a prediction like this. For the neutrinos, you get once you study how the neutrinos can get mass and so forth. In these contexts, again, with very similar ideas, you get half hierarchy because there half of them are coming from 0 modes, but the right-handed neutrinos are what you have integrated out are massive, so you don't get the forgotten distance symmetry, so you get half hierarchy, and this is naturally explaining the PMNS structure that one expects, and you get these kind of prediction for the PMNS matrix. And also you get a prediction for the fact that neutrinos have a normal mass hierarchy. This could in principle be checked because we are on the verge of being able to see whether the neutrinos have normal mass hierarchy or not. And you get estimates for what these masses would be based on these pictures. That would be interesting to. Now the thing I want to point out is that at least there's one instance in which string theory has made a prediction, not a post-diction, which was already verified. Perhaps it's a shock to you. And this is this element here, the theta 1,3 element here, was actually predicted at the time that we were writing a paper on this subject. It was not known experimentally, and theorists were trying to explain why it's 0, because at that time the experimental value was consistent with its being 0. And we had all these ideas of why it's naturally 0 and so forth, and we just came up with this paper where it just this value should be square root of alpha gut, or related to the Caribou angle, basically. And so we wrote our paper, and that was a prediction, I guess, in 2009. We write down theta 1,3.2, and just a few months ago, they come with this prediction, with this experimental computation of theta 1,3 of the order of 0.15. Okay. So if somebody says string theory cannot make predictions, this is one example. Anyhow, there are other ideas for flavor physics, and I don't want to say this is the only one, but this is certainly one such thing which naturally emerges. Now, the CKM hierarchy and the fact that up and down masses, if you want to get the CKM hierarchy as I showed you, you have to assume that the points on the curves where you get up and down masses are not far away from each other, because the CKM matrix tells you what is the basis which is natural at one point on the curve compares with the basis which is natural at the other point. And if these points are far away from each other, then you don't get the hierarchy CKM matrix. You can have hierarchic mass, but not the hierarchy CKM. So you have to bring these points together. If you bring these points together, that E6 point I told you about becomes E7 point. So it seems like, somehow you want to have yet higher symmetry. Why E7? And then once you want to make PMNS work, you find that all the way you have push it up to E8. So without us wanting or liking the beauty of E8 or any of this stuff, just phenomenology pushes up all the way to E8, just trying to explain it. We wanted just SU5. We didn't assume anything more, but just to get the already observed experimental hierarchy of the flavors and the PMNS and CKM and all that to fit in, pushes you back to a 28 point. That's quite remarkable. And in fact, it relates to a question that Witten posed, a good question which is the following. Okay, you seem to say we want to get an E8 point, but what makes that E8 point stable? Because it's bringing points together to enhance symmetries is artificial. In some sense, you want to kind of, generically you would think that these kind of things dissolve and disappear. You push them away, there's deformations or perturbations, this and that will go away. So what guarantees, at least locally, that you won't get rid of this E8 point, even if you have it? So what is the reason for local stability of E8? So this is a very good question, and it's important to find the answer to this question that we still don't know. However, there's talk on understand by Halverson today, and Miriam's talk tomorrow, which may shed light on some aspects of this question related to this involving instantons, which I will not get into. We'll let them tell us their story. So there are also concrete mechanisms to break supersymmetry. Now, most ideas in this connection involve using Euclidean D3 branes. Now, that's natural. D3 branes are very natural in F theory, and Euclidean D3 brane instantons are very natural to study. And there's a whole industry by now developed by a number of groups, which is very interesting, and I think in some sense it's one of the most exciting directions, I would say, of this F theory construction and the development of understanding, which give you a whole host of possible kind of structures that emerge. And the most obvious one is, of course, a D3 brane wrapping around the 7 brane, which is responsible for SU5 gate symmetry in the first place. So you have a natural kind of instanton which goes like E2 minus the volume, E2 minus something which since the volume is related to the alpha gut, you get something like E2 minus the constant over alpha gut already there. And it's interesting to understand exactly this relation and these constants that appear here. And the precise choice of geometry and the fluxes might actually be relevant for understanding these constants. And perhaps more precisely what I want to say is understanding the meaning and the relation of these as potential new scales in these theories. What kind of effects do these instants give? Can they be interesting in new middle scales? Could they give you a scale between the gut scale and the weak scale? Could we just understand them geometrically from understanding these D3 brane instantons? I think these are very interesting questions, and I think it's certainly worthwhile understanding and exploring them. Whether or not the already facts about having the SU5 or the matter structure dictate certain aspects of these instantons that would be relevant. Again, the nice thing I like about this is they are both local. It's a local question, instantons are local, and in principle we could kind of bring them together and see whether there's any prediction that we can make from them. So you could get something, maybe by studying these aspects, you can get something, I'm being heuristic here, about some new scales, which might relate to supersymmetry scale, which might be high or low or whatnot, if we understood these kind of effects better. Another aspect which has been studied is gauge coupling unification or misunifications. We know that the usual grand unified theories for non-supersymmetric ones don't quite work because the couplings don't quite unify the way they should. And MSSM also has a slight mismatch. And so the question is, okay, what will correct these mismatches, or what is the exact structure of the unification? And these morally depend on exotics or loop corrections, one or the other. And understanding what these structures could be is interesting. And of course, in F theory, you have a whole host of possibilities for these exotics, and people have studied it. There are a number of ideas of how that could arise, and methods of how you actually compute the effects of these on the unification of couplings or misunifications have also been studied. But I think they could still be further developed, and I think certainly deserve to be more developed. Now, additional conformal sectors can naturally be incorporated. Again, the D3 branes play the role. Now, instead of instanton D3 branes, you think about the D3 brane as filling the space-time and corresponding to the points in the internal geometry. And so if they're away from any point of enhanced symmetry, if they're just a generic point above which there is an elliptic fiber which is not singular, they look like a boring U1 with an n equals to 4 supersymmetry, extremely boring. But if they somehow bring them to an interesting point with more symmetries, these U1s could have more interesting stuff living on them. Basically, by looking at what stretches between these D3 branes and D7 branes, you get some extra structure living on the D3 brane. And in particular, since I already explained that having a top quark mass means there's an E point, it's natural to ask what happens if D3 brane, also there's D3 brane living at the E point. It's a very natural question, and this has been asked. And it turns out that the theories that you get are related to superconformal theories with E-type symmetry. It inherits the E symmetry there. And it turns out it's related to deformations of Minihan-Nemichansky conformal theories with n equal to 2, deformed to n equals to 1, and with some added bells and whistles that one can study and has been studied. So there's an interesting structure already, somewhat canonically given to us just by the fact that top quark has a mass. We get a very canonical kind of structure of a specific conformal theory coupling. So these are very amusing because we don't have to come up with an arbitrary structure, just very well motivated from the fact that the top quark has mass. We already get led to a very specific class of conformal theories. again, even though they have been studied, they deserve to be more studied, and I think better understood. For example, could they lead to new versions of Higgs mechanism? You see, there are two mechanisms for Higgs mechanism understood in string theory. One is the usual Higgs mechanism, and the other one are the ones involving conformal field theories of the type that have been encountered in the context of point-like instantons for E groups. These are the two different ways that we have seen how the Higgs mechanism can work via conformal points or non-conformal points. And some deformations of the conformal points are interesting potentially for phenomenology, and these are the worthwhile understanding. Thank you. Okay, so now comes the hard questions. So far, these are questions of developmental things. That's nice and theoretical. The question is, what about connection between LHC or data that are coming out from experiments? Well, we don't know. The short answer is, but we can start speculating. Why not? So suppose there's no supersymmetry found in LHC. Of course, we can always push it up, but I think if after a few more years in LHC there's no sign of supersymmetry, I think that, well, I don't know whether supersymmetric components will push it up further or not, but certainly it would be much less appealing to keep on insisting that there's supersymmetry yet and in the next scale. So I think if the supersymmetry is not found, and I think we will know that in the next few years perhaps, well, it turns out one might say that string theory will be completely lost. Now, I wouldn't go that far. Even though most of our constructions or most of our ideas are based on supersymmetry, and we don't really have a good tools to develop what happens when supersymmetry is broken, there are some ideas that might survive. For example, flavor hierarchy that I was talking about, the fact that it's rank 1, happens at the gut scale. That structure, all that you need for that structure is holomorphic at the gut scale. So having supersymmetry all the way at the gut scale is all you need. You don't need low energy supersymmetry for the flavor hierarchy question I was talking about. So it's a bit more robust. So some aspects of phenomenology are more robust that we can still stick to. And I think flavor hierarchy is one area which really deserves to be better understood. So the estimates that I was telling you about in terms of CKM and all that were just the back of the envelope calculation kind of estimates, not really very specific models or this or that. But it would be worthwhile to see actually if you can understand these a bit more in detail, and even for some specific model, just to see what kind of elements come in. Are there very specific relations between PMNS and CKM? Very detailed questions like that. Nobody has studied it, I think, and I think it's certainly worthwhile understanding them deeply, more deeply. So that's something which will still be there, regardless of whether supersymmetry is found. Now, suppose on the more positive note, suppose supersymmetry is found. Well, before I go to that, I should say that if supersymmetry is not found, we should still come up with new ideas. We certainly believe there's dark matter. And up to now, the one way of thinking about dark matter was, the lightly supersymmetric particle. Sounds like a good thing for dark matter. And if there's no supersymmetry, we should come up with new ideas about what we mean by what kind of dark matter structure we can have. And I think that's one of those questions that we don't have at this point any good ideas. So can we come up with some interesting objects which are stable regardless? But again, this really hinges on a bigger program in string theory of understanding how supersymmetry broken vacuum can be handled. Now, if the supersymmetry is found, then it depends on what kind of things we have. If it's, I think most naturally, so there are two possibilities in the context. Well, there are two broad possibilities. One, gravity type supersymmetry breaking, as well as gauge mediation supersymmetry breaking. The more natural one in the context of F theory is some kind of gauge mediation because it is a local question. As I was saying, it's more natural to say you can decompactify gravity all the way. That's the most natural kind of context. And so I think that even though people have contemplated other possibilities, I would say that perhaps one natural possibility is the gauge mediation, or more precisely what one finds is some generalized gauge mediation. And it turns out that using some simple ideas, one can come up with the most, again, the back of the envelope kind of scenarios where it suggests that you have a high-scale supersymmetry breaking involving operators like Judicial-Mazziero operators and And you get predictions like the NLSP, the gravitino of the order of 10 to 100 MeV, and the gravitino, and the NLSP having a lifetime of the order of a second to an hour. So these kind of things, if indeed there's any hint of them in LHC, that would be fantastic. But that remains to be seen, and we don't really know what it could be. Or if there's another possibility that they might have a more exotic Higgs. So Higgs might be having some exotic properties. And then in that context, it's interesting to ask whether this Higgs can naturally fit with the conformal E structure that I was talking about, in which case that would be an interesting possibility as well. So there are two possibilities I see if supersymmetry is found. Either some exotics of Higgs, some Higgs which is not the usual Higgs, some exotic properties, or if it's not as exotic, whether or not you see some other extra prediction of supersymmetry that you expect, for example, for NLSP, the lifetime of NLSP and so forth. And in most models, these turn out to be tau with these lifetimes. Anyhow, so we are on the verge of results from LHC. I guess it's beginning to come out. We'll wait and see, even though currently supersymmetry seems elusive at LHC, but who knows? We have to wait a little bit and be patient. So on that note, I'll stop. Thank you.
Yes, Sakura. Do the Higgs mass, is the Higgs mass somehow preferred in these exotic Higgs models? Is there some range that's, natural?
Well, there's a parameter which tells you it's related to the dimension of the scaling of these operators, and there's some range in which they can be. So it cannot be very specifically tuned, but it turns out that even for a range, I don't remember exact numbers, maybe Yoshi remembers, but from 1 to 1.1 or something, from even a very short range of the dimension of these Higgs. So the Higgs field picks up an anomalous dimension. And if the anomalous dimension is of the order, 0.1 or something, then the Higgs mass could be pushed all the way to 500 GeV. So it's very sensitive to what is the scaling dimensions, and so I cannot really be sure. But it gives you this opportunity. And even if it's the Higgs that's 125 GeV and so forth, there could be the exotics of it, what is the decay rate of it to the photons, and Heckman and collaborators, Piyush and all that, have studied some aspects of these. And so I think, in principle, there are ideas that are ready to be applied depending on what LHC might find.
Peter?
When you look at these global completions of your local models, which sometimes might be needed, you mentioned the T-brains.
Yes.
Yes. Is there some progress along these lines?
Is that what?
Is there some progress along these lines?
What do you mean by progress? You mean
well,
globalization?
I have seen your paper some 1.5 years ago or so.
Right.
And I thought that would be picked up by a lot of people. So I haven't
A lot of people are here.
Did you pick it up yourself?
Well, I haven't picked up my own paper after a while. But I think, as I mentioned, I think it's a very interesting direction, regardless of particle applications. I think T-brains are generalization of brain intersections involving non-abundant flux. As such, they have to be studied. I think for just understanding what T-brains are and what their intersections are. So I think, despite the fact that our paper, I don't know, was 100 pages, it was just barely scratching the surface of the subject, and I think really deserves a lot more work. So I think it's certainly a theoretically interesting subject to study, and the fact that I think it will have, if F theory is correct for application of particle physics, it will have phenomenological applications, so why not?
Bobby?
This decoupling of gravity, I think what tends to happen when you look at how moduli get stabilized, in a compact example, is that you'll get you get strong effects on your local spectrum. So it can really, I actually think that it can change significantly the spectrum, in particular the gravitino, which I think you said is the LSP, will become much heavier typically.
Well, it depends on how supersymmetry is broken, of course. So I was assuming, and I didn't derive it or anything, I was just really assuming it's gauge mediation, or more precisely, some generalized version of them. By that, but then it almost by definition, gravitino will be the lightest one. So just an assumption, really. I didn't prove it or anything. What I meant to say is that it's the most natural one in the context of F theory if you assume that you can have M Planck is infinite, which by definition means gravity can be ignored.
But that is in contrast with having a gut theory, in a sense that there is this tension between decoupling gravity and in a compactification and having a gut theory.
Why? Why is there a contrast? Why is there?
Because when you send the volume to infinity, you're lowering the string scale.
No. This is precisely what F3 is good at and hydraulic string has difficulty with. The 7 brane in which the F3 wraps on has finite volume, even though the full volume of the rest of the geometry could be infinite. You can have a gut which has finite volume because this part is a 4-dimensional subspace of a 6-dimensional space.
But the string scale depends on the overall volume.
The 4-dimensional part of it can be compact. 7 brane is compact, sitting in a non-compact space. So you can easily have a model which has M Planck. So there's no problem in writing a model where M Planck is literally infinite and alpha gut is finite. There's no problem writing down.
Stuart?
So I'm curious, can you get non-abelian family symmetries in F-theory model building?
You can do many things like that, but I think those will be ad hoc. Namely, the family symmetry in this case will be that between the 0 modes, you have an extra rotational symmetry which is not there. Now you can say I will choose a geometry in such a way that the fluxes and the geometry and so on has an extra symmetry which forces to have each time you have a 0 mode, you have 2 0 modes, and then there's a rotational symmetry between them. You could. I would say it's not natural, but I don't think there's a no-go theorem that you cannot.
One more question. Okay.
Yes, again, to the question of Susie breaking and modular stabilization. I agree, if you put the 4 cycle in a non-compact geometry, you can decouple if you want gravity. You can send a Planck to infinity, but in a concrete global model, I mean, because of the value of the gut gauge coupling, which you typically have to satisfy, you sit like maybe 2 orders of magnitude below the Planck scale with your volume of your cycle, right, of your 4 cycle. In that case, you cannot decouple the gravity.
Well, no, I certainly in the real world, you're absolutely right. The M Planck is not infinitely higher than M gut. That's for sure.
It's just 1 or 2 orders of magnitude. It's not much.
So I'm just saying that, the question I was raising was more theoretical. That the idea that you could have taken M Planck to infinity would have said that the questions of unification should be called from gravity. On the other hand, you might say, well, a factor of 100 is not that big. Well, I would say it's big, nevertheless. It's not.
Yeah, but still, I mean, before you make, I mean, when you try to calculate like soft masses or these kind of things, and the effects from supersymmetry breaking, you would have to feed back the effects of gravity if it's just by 1 or 2 orders of magnitude removed from the other scale in your compactification.
Oh yes, no. If you want to have a precision computation,
yeah,
absolutely. But we are still unfortunately far away from the questions of precision. I think all of the things that I was talking about gives you orders of magnitude really, which the first order I think is good enough. But then if you want to have a systematic perturbative expansion and all that, then you have to work much harder.
Fernando, maybe?
What is the status of gauge coupling unification? There were some points on things that you need large thresholds or you need an extra amount of layers to.
Well, there has been, depends on precisely which kind of models you consider. There have been many people actually in the audience who have actually studied that more than I have. But the basic idea is that once you put the fluxes, you can easily get exotics in the geometry, in the solving these matters on the curves. And exotics, as we know, affect it. Now, some people have found that it's natural and it pushes in the right way or this way or that way, or it could and so forth. But that's subject to interpretation. I'm not sure how convincing that is.
Goes from the pyramid same that they meet is essentially is lost somehow.
No, it's not. No, depends on where. Depends on how much exotics you're having and what their masses are. So these exotics are not. Sorry, I should be perhaps more precise. Depends on whether you have chiral exotics or you have non-chiral exotics. So that's what I mean. It's non-chiral exotics that would affect it not too much away from it. So it depends on what's the mass of these exotics.
Okay, maybe one more, and then we should probably wrap up.
Yes. Okay, I have a question about the mechanism for flavor that you discussed, your favorite mechanism. This in the picture, and as far as I understand, this relies on the presence of H-flux.
Yes.
And as far as I understand, this H-flux is not compatible with the Calabi-Yau condition in the equations of motion.
It's certainly not, it's consistent with supersymmetry, but it's not Calabi-Yau for sure.
I think even
you have a deformation of supersymmetry, Calabi-Yau. Somewhat similar to the equation we heard about.
Not even like a torsion, not even SU3 structure, because like a Becker-Becker solution won't even allow, it has to have 2,2, even if you have torsion on it.
Well, certainly there's no a priori problem with supersymmetry. So there's got to be a supersymmetric solution like that. There's no problem. Locally, you can certainly write down.
But not globally.
I don't think there's a problem with globally. You claim there's a problem with writing that globally?
Yeah, because like a Becker-Becker solution, like on kind of fourfolds with any SU4 structure to 3 dimensions.
Well, the reason I think that's a bit strange is that we know G-flux is not a problem with global. Take Calabi-Yau fourfold. We do know that G-flux and with compact Calabi fourfold, there's no problem. At least that's the conventional wisdom.
So what is the H-flux that you mentioned?
H-flux, you can take a limit of this T2 to go 0, depending on which component of the G-flux you take, you get H-flux. Having G-flux is not incompatible with supersymmetry. And therefore,
that to be like 2,1 flux goes to like this particular one goes to 3,1 flux in M theory.
right, depends on which directions you take for your G-flux. There's a 2,2, 3,1, and so forth. Yes.
So this particular one goes to
2,1.
because
Right.
the other one, which is supersymmetric, that goes to 2,2.
Right.
So this particular one, which you have to take here, is the other one, the 1,2, the 2,1, and this goes to 3,1 in M theory.
We can discuss it, but I don't think there's necessarily any problem with global things. But we can discuss it.
Maybe we should wrap this up and continue with discussions during the break. Thank you.